So welcome to Architecture 445. This class will deal with long span structures, what happens when we get larger than the sort of typical spans we deal with in commercial or residential architecture. So above and beyond that sort of 20, 30, 40-foot column bay that you may be used to, and into much, much larger structures, which, as we'll see, get to be so big that we can't just simply scale up the principles that we've talked about in previous classes. We have to do some other things. In today's lecture, 3 parts. The first part, which is this video, we'll talk about what long spans are, kind of definition, why they are both quantitatively and qualitatively different from short spans or normal spans. Go through some definitions, pros and cons, why we have to work a little bit harder to make structures that are bigger, and also talk about costs and considerations. And then in the second 2 parts, we'll talk about how we classify them, both in terms of the mechanics and also in terms of their directionality, whether they're one-way or two-way. We kind of know a long span when we see it. Usually it's a very big volume space, and very often it will have a structure that is very pure. And that's because when we kind of push the envelope, when we push structural principles to their limits, we find that the geometry, the kind of physics, are very defining in terms of what our options are. So here, Eero Saarinen's design for Dulles Airport in Virginia, Saarinen doesn't really have the option of choosing the curvature that he wants. He can pick the size of the towers on either side, but because this is a cable structured system, he's pretty much stuck with a catenary shape, right? A curve that the cables are going to take almost kind of no matter what. So the architecture very often in long spans follows from the structural principles. That maybe we're kind of used to. What we often don't think about right away is the fact that these long spans, even though once they're built and monolithic, behave in ways that sort of define them as long span structures, we also have to go build them. And so a lot of the problems that we deal with go beyond just the simple structural performance and deal with how we make a really, really big thing in often little pieces, how we get those pieces to the site, how we stick them together in ways that will make them all behave as one big monolithic structure. So for example, Pierluigi Nervi's work, great Italian engineer and builder, we can look at it sort of squinting and say, oh, here's a funicular shape, it's an arch, it's roughly a catenary arch. In other words, if you take Saarinen's airport, flip it upside down, you get Nervi's Alla Paolo. However, if you look closely, you can see that this funicular arch is made up of hundreds of little components, all of which are hand fabricated, have to be brought to the site, have to be lifted into place. And if you think about it, that structure has to stand up both when it's finished, which is fairly easy, right? A funicular arch is going to stand up pretty much on its own. It also has to be stable while it's being constructed, before it is one complete piece. And we'll talk a little bit about construction methods and how we deal with these kind of problems as we go forward in this unit. Why do we build long spans? Answer sometimes is pretty obvious. We very often need spaces that are column free. We may be designing a sports arena. Nobody wants to sit behind a steel or concrete column while a basketball game's going on. But we may also find that the program, the functionality of the space, demands bigger and bigger spans. So for instance, we might be doing a recreational center or an exhibit hall where we can put columns some places but not others. Some of that building may have a very conventional 30 or 40 foot column grid. Other spaces, we may have to get columns out of the way, or we may need additional flexibility in the way the floors are configured. And in those cases, we may find ourselves dealing with 60, 80, 100-foot spans, and we may be beyond the realm of what we can easily do with simple beam theory, right? Simple spanning elements. Often, the long span programs that we really think about, things like aircraft hangars, will have a very defined long span, right? The wingspan of an aircraft, maybe also the height of the tail that we have to get up and over. Other times we may have some balances to make. We may be doing a factory building where there will be some trade-offs between the bigger open spans that maybe we want functionally, and the costs associated with those. And we may find that there's a happy medium where we have some long spans, some regular spans, or where we compromise and have maybe sort of middle spans. So today we want to really talk about three things: what a long span is, how we define it, why we use them, and reasons that we might not use them, the sort of drawbacks to going beyond the kind of safe, comfortable spans that we're used to. To do that, let's start by talking about what happens when we get quantitatively larger. Right? When we design beams, for example, that span greater and greater distances, you may recall from our exercises in beam design that we always had this moment where, after we had solved the problem, right, figured out whatever maybe steel beam we need to span a distance, we then had to go back and add the dead weight of that beam into the equation, right? Do the equation over again, see if the beam could carry not just the live load that we were putting on it, but also its own dead weight. And if we go back to the Renaissance, Galileo was the first one to realize that when we blow things up, we're not just increasing the kind of sectional scale of them, we're increasing the volume. And so if, for example, to use Galileo's famous example, if we were to take an animal, a dog say, and make that dog like twice as big, right? We would actually be increasing the volume of the dog by a greater factor than the cross-sectional area of the dog's bones, dog's skeletons. So to hold the dog up, to hold that greater quantity of dog up, we actually have to increase the size of the dog's bones by the cube, not by the square. We can't just keep the same proportions, the same sectional proportions, the same two-dimensional proportions that we're used to, because we're increasing the volume and therefore we're increasing the mass of the structure exponentially, by the cube instead of by the square. So Galileo's great kind of realization, and this is really key to structural engineering, is that the ratio between the area and the volume changes at different rates when we blow things up. So when we're designing a beam, for example, we're adding not just kind of depth to the beam, which is important, but we're adding volume to the beam, and therefore we're adding weight. And as you may remember, we get to spans where steel beams can't even carry themselves, right? They're carrying their own dead load, and as we increase the depth of the beam to carry that load, we're increasing the mass and the weight that the beam has to carry. At some point, we kind of start chasing our tail, right? We're adding more weight to that beam than we are adding efficiency or effectiveness. So we have these kind of two ways of thinking about long spans, right? One of them is simply to say that, yes, there are quantitative differences between a short span and a long span. And conventionally, we say that this is around maybe 60 feet, right? Once we're beyond 60 feet, we're into sort of specialty structures. But maybe more important than this is to think about Galileo and to think about a qualitative definition of a long span. In other words, the types of structures that we're dealing with. Anything where we get beyond simple beam theory, right? The flexure formula, section modulus times strength of material equals allowable moment. Anytime we get to a point where the section modulus starts getting harder and harder to get without adding a lot of load to the system, a lot of dead weight to the system, we're in what we think of as a long span. We have to do something either to hack that beam or to come up with a very, very different system of structural spanning. Now, the reason that I would argue for a qualitative definition is that we also, on the other end of the scale, sometimes see structures that feel like long spans, even though they're relatively small. So here, for example, is a great concrete shell by the Mexican builder, architect, engineer Felix Candela. And Candela here has a great program where the astronomers need a very thin roof so that they're not intercepting the cosmic rays that they're trying to study. There can't be any steel in the shell of the roof. And so Candela designs this very, very thin, about 3/4 of an inch thick concrete with no reinforcing in it. and drapes it over this parabolic or catenary shape. You can see if you look closely, it's got a positive curve in one direction and negative curve in the other. We will talk a lot about this when we start talking about shells. But if you look even more closely, what you see is that this is actually a very, very tiny building. It's only about 25 feet across. Is that a long span? Well, quantitatively, no, it's not a long span. It's a relatively short span. But candela here is beyond simple beam theory because that roof has to be so thin. And so it's not just about the kind of actual distance that the thing is spanning. It's about the fact that he has to resort to a very, very different way of spanning because a simple beam and slab would require too much reinforcing or too much thickness in the concrete. So here I think a great example of what we might call a short long span, right? A quantitatively small span that nevertheless has difficulties with it that we associate with longer span construction. So because of Galileo's square cube law, right, because we're carrying the weight of the spanning element in addition to the live load, and because the bigger that element is, the heavier it is, the harder it has to work, what we find is that long spans are basically an exercise in trying to reduce weight, trying to take elements and to make them as efficient as we can so that they can use most of their effectiveness basically carrying a live load and less of it carrying their own dead weight across a span. So we're looking for very, very efficient systems. We are doing this basically in two directions. If you think about a simple beam, we talked about ways that we could tweak that beam's shape longitudinally along its axis, but also in cross-section, right, across the short axis. So if you look at the examples here on the right, if we take a very simple rectangular beam, you may remember that we talked about how inefficient this is because so much of its mass, so much of its weight is being carried right around the neutral axis, right around its middle. All of that material close to the middle of the beam is lazy, right? It's not really doing much work. So the logic of an I-beam, or a W shape, is that we're really deploying that material where it's going to work the hardest, in the flanges, the areas of greatest tension and compression. And the I-beam shape is based on putting as much material at the far edges, remember the farthest fiber of the beam as we can, and minimizing the amount of material in the web, in the kind of lazy area closer to the neutral axis. Now, a very, very simple long span technique would be to take that I-beam and to castellate it, to cut a zigzag line through it, to take the resulting two pieces, shift them by one phase, and get basically a kind of supercharged I-beam, where the flanges are further apart, right, because we've expanded the beam basically. We've taken weight away from the neutral axis. Note that those open hexagons that come from that zigzag cut are basically removing weight from around the neutral axis, the center of the beam where it's least effective. We're taking the same amount of material, therefore the same amount of weight as in this I-beam, and we're deploying it more strategically, more effectively. We're basically getting a deeper beam for the same amount of weight, and therefore it's going to be more efficient. Able to carry more load because it has a higher section modulus, able to carry that load more efficiently because it's adding less of its own dead load to the system. If we want to push this even further, when we talked briefly about trusses, we talked about the fact that a truss is basically two flanges, right? A tension flange on the bottom, if it's simply supported, compression flange on the top. And then instead of the web of an I-beam, a truss just basically has this network of triangular panels, chords that form triangular shapes. And what those chords are doing is making the two flanges work in tandem. They're taking the place of the relatively heavy web. And so note that now we have maybe an even greater depth with maybe even less weight, right? This is why a truss is such an effective long span element, because it's basically making an I-beam with a web that weighs almost nothing, right? Putting almost all of its material into the two flanges. And if you want to push this to an extreme, we could do something called a king post truss, where we really separate the cords into one long tension element, a cable in this case, and one compression element, right? Here's a flange, and then instead of the triangulation of the truss, we just have a single cord, a single king post that creates that distance between the tension element and the compression element. Now, that is super effective, but we're not only designing, remember, for strength, we're also designing for deflection. And so the lightness might be quite good, but we may find that in a king post truss, we have a very, very lively structural member. Maybe that's okay for a roof, probably not so good for a floor. The less weight we have in the structural element, usually the less stiff it is, or the more prone to deflection. And so we're going to have this constant battle where, as long span designers, we want to decrease weight, increase efficiency, push the envelope as far as we can, find as many little structural hacks as we can come up with. At some point, we're going to run up against the fact that our structural element is flimsy. And even if we can design it to be strong enough, it may not be serviceable, right? It may have more deflection than the function that we need it to have allows for. It may be too lively, right? It may bounce, and we hate to have things like floors bouncing. Somewhere in this palette, there will be the kind of ideal solution, right? That balances the need for lightness with the corresponding or contradictory need for stiffness. When we get to bigger spans, it's not just the weight that's the issue. We have all of these other basically qualitative issues that come into play because the spans are greater, they get more and more complex. Maybe first and foremost of this is integration and coordination. Trying not only to work with a structural engineer to develop an architecturally appropriate long span, but also, for example, a civil engineer who may have greater foundation loads to deal with than we're used to. Talking with cladding engineers who may have to attach their system to a structural system that maybe is quite lively, right, that moves around quite a bit. You can see here on site, this is a photo of the TWA terminal by Eero Saarinen under construction, and you can see the difficulties of casting a very, very complex, heavily reinforced shell in place. All of these workers have to have uniform numbers so that everyone knows where every member of the team is, right? A kind of logistics nightmare. The complexity of construction is matched by a greater risk. Anytime we make bigger and bigger structures, we run greater and greater risks of failure, right? And catastrophic failure in particular. In long spans, we're sort of putting all of our eggs in one basket. We may have an arena that holds 14 or 15,000 people. If something goes wrong in that, that's a potential for a really, really mass casualty incident. So the risks are often much greater with long spans in addition to the difficulty of coordinating them. They are hard to build. We're trying to get big structures put on site, and of course we have to deliver them to the site either in little pieces or in concrete trucks. How do we arrange a very difficult, often very lengthy construction process? The costs, we'll talk about these in a second here, go beyond just those of the simple material. We have costs associated with the construction process and the fabrication process. We're very often stretching materials kind of to their limit. So we may, in addition to all of those structural engineers, we may have material scientists on board who are trying to help us to hack the actual material. This comes with costs and risks as well. And finally, a couple of issues that I'll talk about a little bit more today. Connections. When we have hundreds of pieces coming together, we have to think very carefully about how those go together, both in terms of efficient construction and effective long-term performance. And then two that we often don't think about but really need to, we're talking about big spans, materials that, like all materials, expand and contract in heat and that deflect under load. So we are really, when we're designing long spans, we're designing for static performance, but what we really end up with are almost kind of live animals, right? Structures that are growing and shrinking on hot and cold days. structures that are moving under wind forces maybe more than we would expect, and structures that are subject to, in concrete in particular, things like creep, right? The fact that over time, there's a very, very small percentage of deflection in concrete structures that comes from the fact that concrete never stops flowing. It just slows way down. Even though these are very, very minor percentages, when we have very, very big spans, that may be a matter of inches, right? 5 or 6 inches in a long span isn't unusual to plan for in terms of deflection. That's an awful lot when you're trying to connect a structure with something like a curtain wall or interior finishes. The materials that we use for long spans are usually pretty limited. While we'll see some timber long spans, we generally face issues of deflection and stiffness in timber that are very, very hard to deal with. And so almost all of our long spans are going to be either in steel or in concrete. We're looking for, obviously, a good strength to weight ratio. Weight is the killer issue in long spans. We want to reduce that as much as possible. But we're also looking, again, for stiffness. So even though we think of concrete as a very, very heavy material, often we're up against issues of stiffness that demand that we use it just because that's the only way to meet the deflection criteria that we're after. We're looking at the ability not just to assemble it, but also to fabricate it. So how do we make it? Do we do some of it in the factory, some of it on site? How do we get all of these pieces to the site and joined in a way that makes them into an effective structure? And as I mentioned before, thinking about thermal expansion, steel expands and contracts much more in hot and cold weather than concrete does. And so if we're going with steel, we have to worry not only about stiffness, but we also have to think more about how that live structure is going to grow and shrink over the course of a typical year, weather-wise. And then finally, how do materials fit with the geometry or the long span system that we come up with? The most infamous example of this is probably the Sydney Opera House. The architect, Jorn Utzon, has this idea about a spherical geometry that he thinks will bring a kind of aesthetic unity to the project. A sphere, of course, is a terrible thing to have to engineer, but it's also a really, really hard thing to build if, as was the case in the early 1960s, you don't have all the computer support that we have today. And so even though the Sydney Opera House was built, it faced cost overruns that famously almost bankrupted the country of Australia, right? Is that a success? Well, it's certainly a successful building. The process that relied on this kind of flawed geometry, right? A mismatch of geometry and materials is generally thought of as a construction failure, right? Because its cost overruns were so great. In addition to thinking about the material, though, we have all of these other issues that start to affect us when we get to bigger and bigger scales. The actual cost of the steel or the concrete or the timber or the fabric or whatever we're using for long spans is usually very, very small compared with the costs of fabricating it, bringing those pieces to the site, putting them into place, and staffing the process, right? The labor costs are often prohibitive when we're talking about long spans. We have to look very carefully at what materials are available, but also what regional differences there are in how those materials get fabricated, brought to the site. Is there good infrastructure? How much skilled or unskilled labor is available, and how much does it cost? And so here are a couple examples of long spans. If you're designing an airport in London in the 1990s, labor is relatively expensive. So most of Stansted Airport was actually kind of put together in the factory, shipped out in ready-made pieces, assembled on the site, lifted into place, right? A very kind of industrialized process. If, on the other hand, you're Eladio Dieste and you're working in Uruguay in the 1950s and 1960s, labor costs are very cheap. And therefore, you might switch to a system that relies much more on handicraft than industrialization. Uruguay in the 1950s doesn't have the steel manufacturing capabilities that London in the 1990s does. And so Dieste figures out a way to build these long span warehouses of his, not out of steel, not out of concrete, but actually out of masonry. right? Long span masonry that today we think of as very beautiful and poetic, but slightly strange because we're not used to seeing it. Actually, in D'Este's case, it makes perfect sense in the economic conditions that he's facing in the 1950s, 1960s. Labor is usually the determining cost in American construction. We have very, very high prices, particularly for skilled labor. And so anything we can do to reduce the amount of labor on the site is going to mean a less costly structure. We are going to try to prefabricate as many of the elements as we can, think about ways to get them to the site as fully formed as possible so that what happens on site can be very, very quick, right? Bolting things together, attaching things, not actually making things on the job site. In long spans, this is complicated by the fact that we need specialty construction equipment, very, very large cranes that have to move big pieces around. And what we may find is that there's a trade-off between the size of the thing that we can make in the factory and the size and time it takes to lift a big piece or to lift many, many small pieces into place on a job site. The trade-off we'll often find, right, zero-sum game between time and cost. If we break the thing down into very, very small elements, we'll need a smaller crane, but it may take much more time to put all those elements together. If, on the other hand, we prefabricate the long span in very, very big portions, it may take less time, but we're going to need more specialty equipment to get it into place. We don't often think about this, but in the back of your mind, you may realize that we actually have to get all of these pieces to the job site. If we're designing a bridge, that might be very easy. We might be able to get very, very large pieces into place on barges. Architects usually are working with landlocked sites, and so everything that we put into our building has to show up basically on a truck. And there are limits to the size of things that we can put on highways in particular. So 60 feet is a standard maximum length and a maximum height of 14 feet. Although if we're shipping by truck, usually that's only going to be more like 10 or 12 feet. So think about this. If we're designing long spans that are 100 feet, 200 feet, 300 feet, we have to find ways to break those down into elements that can be fabricated in much, much smaller pieces. This obviously limits what we can do. We have to think about how those pieces get not just shipped, but also connected. If you think about it, though, it also means that we're necessarily working with a kind of grain and a kind of pattern. If we have to break these long spans down into these smaller elements for construction, this is one thing we can think about as architects to add that kind of human scale to a long span that we seem to like, right? That our eyeballs seem to like to see. The other problem with this is that we have to put all this stuff together, and we have to rely on connections that are both quick to assemble on site, but also robust and reliable over the course of the structure. Most long span failures take place where elements are connected. Spanning members themselves don't very often fail. It's usually how they are attached to one another. We may be relying on the kind of overall monolithic behavior of the structure to hold it up, which means that as we're building this structure, we may have a very, very flimsy building that we're putting together. And so we have to think about not just designing the structure to work when it's complete, but how it's going to stand up on the job site when it is incomplete, how we maybe temporarily brace or scaffold it. The other thing is that no matter what material we're using, we're going to have a certain tolerance, much, much tighter in steel than in concrete, but nevertheless still there. That tolerance builds up over a long span. And what we may find is that we have to have places where we can actually adjust, where we can slide things or move things, shim things, so that we're maintaining the structural geometry that our engineers want. And finally, because connections are prone to failure, we want redundancy. We want multiple load paths. We want long span structures that behave more like networks than like individual pieces. We have to think too, not just about the safety of the structure when it's done, but as you see here on the lower right, the Centre Pompidou in Paris being assembled, we have to think about the safety of the construction site itself. And this would never pass muster today with job site safety laws. Not only is the guy not wearing a construction helmet and smoking on a job site, which we wouldn't even think of today, but you can see that there are going to be real issues if that piece that he's attaching starts to move or starts to swing. Connections are vulnerable not just to failure in the long run, they're vulnerable to problems that happen during construction as well. And today we would want to think about this worker and how basically to protect his vulnerable arms and hands from large pieces of steel kind of swinging around. And connections too emphasize, I think, the fact that long spans are both high reward but also high risk. They can be very, very efficient, very effective ways of spanning space. They can also be really dramatic ways of doing this. But when we put all of our eggs in one basket, when we design larger and larger spans that are going to hold more and more people, we have greater and greater responsibility. This example is really close to home. This is the Hyatt Regency in Kansas City. In 1981, two of those long-span bridges over the atrium collapsed, and it was down to a faulty connection. It hadn't been engineered wrong, but it had been changed by a contractor. Problems with that connection had not been apparent in the review process, and in one of these evenings when the bridges were crowded, two of them actually came down. 114 people were killed. So this is a very, very real issue that we deal with, that the long span has great potential, but it comes with really, really great responsibility. And it also comes with great complexity. And that complexity, the possibility that things will go wrong without us fully understanding them, is always there. So a couple examples that I think really bring home the potential for this and also maybe emphasize these themes, right, of lightness, of transportation, of fabrication versus assembly. Two bridges. This one in Norway, up in the mountains, very, very inaccessible site. And so the architects and engineers come up with a really unique strategy for transportation, fabrication, and assembly. The entire bridge basically is made in a factory, and it is lifted not by individual trucks, but the whole thing is picked up by a helicopter, sky crane, lowered into place. There's a very narrow window that helicopters can operate in the mountains. The weather has to be kind of perfect, no wind. So they have this kind of 20-minute window that they can get the bridge flown in, put in place, and then a very, very small team of construction engineers on site actually attaches it to the foundations. Now, a couple of things to point out, right? One is that this takes the need for lightness to an extreme. Not only are we worried about the dead load of the bridge when it's in place, but obviously the engineers here have to worry about how much a helicopter can actually carry. You may have noticed that the deck was actually installed after the structure was brought in, right? So to save weight for the helicopter. But you'll also notice that even though there's kind of precious little quote-unquote architecture here, it's an architecturally dramatic structure, right? Those constraints have made the bridge really, really elegant. They've forced decisions about structural geometry. Notice all the triangles. They've forced decisions about appropriate materials to appropriate behaviors. So notice that the cross bracing is all in tension cables. The verticals are what we would think of as compression cords. Those are all in cylindrical pipes. And notice too that the connections, everything that's done in the factory is very, very tight. The connections to the mountain itself are relatively crude, right? It sits on a couple of relatively bulky concrete foundations. So minimizing the amount of on-site work that needs to be done. The real emphasis on saving weight has forced decisions that have made for a kind of, we might call it like a forced elegance. Now, I'll contrast this with another set of bridges These bridges are in remote mountain villages in Peru, where for centuries villagers have come together every couple of years. They have woven grass into these giant ropes and cables, and they have used those ropes and cables to create suspension bridges across some of these gorges that enable them to go from village to village without having to descend into valleys or without having to cross rivers. Now, this is a very, very different balance of material availability, labor costs, and structural performance. In the case of these bridges, the labor is free. The villagers all agree that every couple of years they're going to take a few days and basically collectively fabricate and build the bridges. The material is also free. They use native grasses that are just right there and available. The structural performance, compared with the bridge in Norway, is relatively poor. These are really, really bouncy bridges, and they don't last forever. They have to be replaced every couple of years because the grass starts to rot. Nevertheless, right, these get the job done in similar ways, right? They are perfectly fine for one or two people crossing at a time who are used to walking across bouncy bridges. The villagers in Peru clearly do not have access, or at least not easy access, not cheap access, to steel or to industrial fabrication, or certainly to a helicopter. So this is a very resource and labor appropriate way of getting a long span that probably wouldn't have worked in Norway. Nevertheless, if you look at these two bridges, I'll just go back for a second, you see that the long span is forcing kind of pure structural shapes, right? Triangles, cross bracing in the case of the Norwegian bridge, and this funicular hanging cable shape in the case of the grass bridge in Peru. I would hold these up as two examples that as you're going through the labs, doing your own long span design work, you think very carefully about this balance of performance, material, fabrication, assembly, and labor. All of those combine to create long span structures that are more efficient, more effective. And both of these, of course, are concerned with saving weight, right? Reducing the amount of dead load that the structure itself contributes to the system. Okay, so that's a very brief introduction, what long spans are, how we think differently than when we're just designing in beams and columns, reasons that we might be hesitant to use some of these techniques, and some of the things that we think about in terms of cost. In the next video lecture, we'll talk about classifications, how we think about long spans in terms of the structural classifications that we've talked about all along, whether we're using the form, the section, whether we're using a network of vectors, or kind of a new one, whether we're thinking just about how things can flow or how we can make forces flow across surfaces.